Section 4.5 talks about exponential functions. Functions. Um, we will recognize and write equations for exponential scenarios, identify and interpret the initial and the constant ratio, describe what a solution means in the situation, graph growth and decay, create an equation for an exponential function, and we will also use a graph to predict some values. So I have a couple of recalls here. First, I would like us to recall that the slope of the line, okay, it's been a little while, but we still remember the whole unit that came before this was the constant change, and it was a constant add or subtract. It was also called M. It was the change ratio of change in response to, I don't know why I put a period next to that. I did not shorthand it. To the change in the explanatory, I will shorthand that. So dependent to independent ratio. And there is a formula where it's here's the change, find the difference, and here's the change, find the difference, and then find the ratio. Okay, and this was the constant addition or constant subtraction that kept happening. I also want to remind us that lines are I like to call them first layer pattern of a constant addition. So what I actually just said, or constant subtraction. Yeah. You just go down the chart. If there's a constant add or constant subtract, then you know it's linear. And we know that lines are, I'll just write that for my next comment. Yeah. So lines are modeled with y equals either mx plus b, or I like b plus mx, the initial amount plus the constant rate of change however many times. Or, right, we had a very specific case of y equals kx for direct variation. So when that initial was 0, when b was 0. Okay. And I also want to recall our inverse models from section 4.4, where inverse variation models with y equals k divided by x, okay, where we're dividing by the variable, and where you find k, and the pattern was increase, decrease, decrease, increase. So where you find k to write an equation, find k, constant number, and it has the increase, decrease, and decrease, increase pattern. Okay, high, low, high pattern. Okay, so example 1 talks about some patterns. Let's do it. Right on. Find the pattern, fill in the table, write an equation. I already see it. And I think we've seen this example before, actually. I see the pattern is a constant plus 5 for every 1 increase in year. Okay, I'll fill in the pattern. 5 more makes 27 price in dollars. 5 more makes 32 price in dollars after 6 years. And write an equation. Pretty good at this by now. Price, because it's linear. So linear. Whatever. Right? It has the constant add or subtract. So I know that the initial is 2 and the pattern is add 5 however many times, which is however many years go by. Okay, P equals price in dollars, T equals years since 2000. Got it. Linear pattern. Check. I like it. Makes me feel good. And then let's see. Find the pattern, fill in the table, write an equation for this. Oh, biscuits, what is happening here? Okay. So, I see big price, small year. I see small price, bigger year. So I see this increase, decrease, decrease, increase thing that they were talking about in inverse variation. Can we see a relationship? So I do see the increase, decrease. And so maybe I'll write it like this. The big, big, small, and small, big. So what I mean by that, so they write it like that, but my brain has to process it actually like this. When one is big, the other is small. And when one is small, the other is big, is what they mean. So reinterpret it. I don't like it increase, decrease, but I like it more like when one is big, the other is small. When one is small, the other is big. And that's why it's called inverse. Swappy-doo. Let's see. So that means I have to start with that model. Okay, but I don't have Y and I don't have X. I have years and I have price. So I would put price and K, and I would put time for years. So I just morphed it into the situation. And then our first job is to find K. So because this is a constant number, so let me pick a price, 12 equals, we don't know K yet, but we do know the time is 1. Oh, look at that. K divided by 1 is just K. So this K is 12. I want you to know, as a side note, if I had done this with any of these numbers, it would have worked. So let me just pick this 3 and this 4. Price 4, there's K, and years since time is 3. Well, K is being divided by 3. To undo that, we multiply or scale up both sides. So scale them both up by 3, magnify that by 3, and you get 12. Magnify this by 3, and you're not portioning it down by 3, so you have K. So just a side thought that you could have used any of these P's and T's to get that constant K of 12. But that means our model is really, so this was inverse variation with a model of P equals 12 divided by T, where P is the price in dollars and T is the number of years since 2000. Okay, now we have a totally different scenario. And so just so that we can compare the two, right? The linear had the constant increase pattern. This one had this big, small, small, big pattern, 2 different equations. Here, that was the linear model. And over here. This was the inverse variation model. Okay, now let's suppose we have a different scenario. We have minutes elapsed, number of bacteria. Okay, what is the pattern? Fill in the table. I see +6, +12. So it's not linear. So not linear because it went +6 and then it went +12. Okay, got it. Not linear. Done. Here, maybe I should go. Okay. And then I have to see if it's small, big, big, small. Small, big, small, big, small, big, small, big. So no, it is not big, small, small, big, or small, big, big, small. It is not that. It is small to big, small to big, small to big, small to big. Okay. So it's not inverse either. And we're not told it is. So not inverse variation. Okay, so then we are on our own. We are left to our own devices to figure out this pattern. But I do see a pattern. Like 6 times 2 makes 12. 12 times 2 makes 24. 24 times 2 makes 48. These are doubling. So the pattern I see is times 2. So to think back to the exponents section, like in 1.7, back in chapter 1, where we talked about exponents and scientific notation, about when we're doing constant repeated multiplication, we're really dealing with exponents. So let's fill in this chart. Oh boy, here, just to make my life easier. Double it again, 96. Double it again, 192 bacteria after 5 hours. Double it again, 384 bacteria after 6 hours. And there is our pattern. It says, write an equation for this data. Okay. Because this, so just to look or think back to 1.7, this was 6, this was 6 times 2, this was 6 times 2 times 2, or 6 times 2 squared. This one we doubled again, 2 times 2 times 2, 6 times 2 cubed, and this is 6 times 2 to the first, and this is 6 times scale up by 2, no times. Okay, equation. So I would say B is equal to 6 times 2 to the T, where it's doubling every time, but now I used an exponent because it was constantly doubling or multiplying by 2 each time. So a couple of remarks. There's too many papers on my. First remark is that lines, okay, so lines have the response variable is equal to the initial plus the constant change times the explanatory variable. How many times did that constant change happen? So it was B plus MX, okay? And that was the constant add or subtract. Okay, this one is different. The inverse variation, inverse variation had looked like the response was equal to some number K, okay, a constant number divided by the explanatory variable, and which would equal K X. And this one, so this was constant add or subtract, but that one, when we're thinking about it, is small, big, big, small. I don't know if I mean, I don't want it to look like division or subtraction. It's just a relation. Um, okay. And what's remarkable now is that we have these exponentials. So exponential. Okay, so now we have this situation where we have, let's see, here's our initial. So the response, which is the bacteria, will equal, that was the initial number of bacteria, initial, times, that is the pattern, but it's a constant, not constant add or subtract, but a constant multiplier. So, okay, say that, constant multiplier, okay, and then to the variable, to the explanatory variable. So that's in the exponent. Or if we wanted to rewrite it, maybe we could rewrite it as the initial, which is B. I'm not going to rewrite it right now, but I am going to say that this was the pattern was a constant multiplier. And my last kind of comment here is actually kind of a warning. Beware that many people accidentally get mixed up with exponents and multiplying and all that jazz. So x squared is x times itself. You know, for instance, 3 squared is 3 times 3. And these are like squares. Yeah, like this would be a 3 by 3 square with an area of 9. Or an x by x square with an area of x squared. Versus 2 to the x. So if we put a variable in the exponent now, we need to be careful not to flippity flop these. And this really represents 2 being multiplied times itself x number of times. Okay. And also doesn't represent 2 times x in either scenario. For instance, 3 squared is not 6. So I just wanted to kind of lay those out. So maybe I would even write that versus 2x, which is really x plus x, or x added 2 times. Okay, so in the next video, we will do an example where we'll see this kind of thing happen. This exponential looks like it's going down happen.